Okay, let's start with the feasible and decent directions now. So, suppose this is my optimization problem. Minimize fx subject to x belongs to capital X, right? Where x capital X is my feasible constraint, feasible region in a way. So, I define a feasible direction. Let's define it. So suppose if I have a vector d, right, a vector d which belongs to maybe like it's a n dimensional vector, okay, and d is not equal to 0, then it is said to be a feasible direction if if there exists a delta uh, greater than 0, such that x plus alpha d is also belongs to capital X for all alpha belongs to 0 to delta. Okay, so this basically means what? It means that suppose you have this particular set X, right, and suppose your X is this particular point, right? So for all delta greater than 0, you can actually find a direction in which you can move and you still remain in set X, right? So this is my set X, feasible set. So and this is my small x. If I move in this particular direction, I'll still be in the set. If I move in this particular direction, this direction, this direction, this direction, in all the cases I'll be in the set. Suppose if I choose a point, say here, if I move in this direction, I'll be in the set. However, if I try to move in this direction, I'll end up outside the set. Okay, so the set of all the feasible directions for this particular x is in this direction, right? So I can define a feasible direction again for a particular x in a way that uh, for a delta greater than 0, x plus alpha d lies within the set capital X for all alpha which lies between 0 and delta. Okay, so now uh, so let's say that the uh, that this particular set f, capital F of x, is the set of all feasible directions for a particular x. So set of all feasible directions for x belongs to capital X. Okay, now let us define decent direction. So direction basically means what? You move in a direction and you in your value of the function f decreases, right? So if I define decent direction, with respect to x for a particular function f, right? So it again means a vector d, an n-dimensional vector d, such that my d is not equal to 0, and it is a decent direction if there exists a delta which is greater than 0, such that f of x plus alpha d is less than or equal to f of x for all alpha belongs to 0 comma delta. So this means what? That suppose this is my function f, right? And if I am at this particular point x, if I move in a direction which decreases the value of my function f, that will be a descent direction. So for this particular x, this is a descent direction, right? This particular direction is a descent direction. For this particular x, this is a descent direction, right? So I mean descent direction in terms of, so in this case this is the descent direction, in this case this is the descent direction, right? So similarly you can define a capital D. Let me make a good D of x is the set of all descent directions at x with respect to basically a function f, right? So you'll note that a direction can, like for defining a feasible direction, you don't really need a function f, right? In this case function f is not needed. However, in this particular case, when we're defining descent direction, we need function, we need to define it with respect to a function f, because we are talking the descent direction in terms of function f. So if the function f changes, the descent directions will also change for a particular x, right? So so yeah, again in this case x belongs to capital set X. Okay, so so let us see a theorem. I'll just state the theorem without any proof, and basically I'll give you some intuition behind it. So the theorem is like, let x be a non-empty set in x, let x be a non-empty set in Rn. Okay, let x be a non-empty set in Rn, and x star belongs to capital X, is a local minimum of f over x, then the set of feasible directions at x star intersection set of descent directions at x star, intersection of both of them will be a null set. So this is a very important theorem. So this basically means that if you are at a local minimum with respect to a function f over x, right, then you cannot find a direction in which you move so that you are in the feasible region, as well as you move down the function f. So this is what we generally want, like, right? So if I am at a local minima, I don't really want a direction in which I move and I still reduce. So suppose this is a function, right? And maybe I'll make a better function. Suppose, I don't know. Okay, and the function is defined in this particular range, right? So if I am at this particular point, if I'm at this particular point, uh, although for this particular function f, the descent direction is in this direction, however my feasible set is not, like if I move in this particular direction I cannot still remain in the feasible set, right? And let's say again this is my local minima, right? Then suppose if I move in this particular direction, my value of the function will not reduce with the x, although I'm still in the feasible direction. For this particular x, my set of feasible directions are these two directions, however none of them is a descent direction, right? So I've just stated the theorem without any proof, however this is the intuition behind it, that you cannot be in the feasible set and move in the descent direction at the same time. Okay, so let's see how do we quantify, or how do we algebraically write set, like how can we find set f and set d. Okay, so let's start with the descent set of descent directions, right? So suppose this is my function, right? The function f, right? And at a particular x, the gradient of the function gives me this particular direction. So this is grad of fx. This is my function f, right? And this is at the particular point x. I can find gradient of x. So if this is the direction of gradient, this is the direction in which I'll move down, right? So if I can find a particular vector d, suppose this is my direction d, if the dot product of this particular vector and this particular vector is negative, so basically my angle is obtuse, then this will be a descent direction. So basically if I can find a d such that the dot product of gradient and the direction d is less than 0, then this is a descent direction. Right, however note that this will not really give us all the descent directions, so we'll just say that this particular set is d bar of x, right? So another way of seeing of if you're not really convinced this way, you can also like see it this way, that if my f transpose f gradient of f transpose d is less than 0, then basically what I can do is I can write it like this: f of x plus alpha times d minus f of x by say alpha, and limit alpha tends to 0 is less than 0, and right, since alpha is positive, let us consider it is positive, right? Then f of x plus alpha d is less than f of x. Right, so my d is a descent direction. So but this particular, I'm not sure if this particular direction is the entire set of is the entire set of descent directions. So I'll just say that my d bar of x is a subset of set of all descent directions. Okay, so now let's see how do I algebraically write the feasible directions. Okay, so suppose let's consider this particular problem. Consider this problem. Minimize f of x subject to h of hj of x less than equal to 0 for all j equals to 1 to up to l. Okay, and my x belongs to Rn. So like again we'll assume that hj and f are sufficiently smooth, right? So I define a set called, or I define active constraints, term called active constraints, for the set of all the constraints which are 0 at that particular point. So active constraints are the set of all constraints at a particular x such that those constraints are 0. So suppose if I have this particular example, let's take this particular set, right? And my x is at this point right now. So, and let us define all the constraints as 1, 2, 3, 4 and 5. Okay, so if my point x is at this particular point, then only this fifth constraint is active right now. This is my feasible region. Only constraint number 5 is active. Now let's see, if I place my point x here, then the constraints 3 and constraint 4 are active at this particular time, right? And if I consider an interior point, then no constraint is active. So basically at any interior point, active set is null set. Okay, so so basically there's again a lemma which kind of which I'll prove, like I'll just state without any proof, however which it'll help us to write algebraically a feasible set, okay, a feasible direction, sorry. So the lemma is something like, for any x which belongs to capital X, the set of feasible directions, sorry, is a set such that gradient of h at x dot product with d, if it is less than 0 for all j which belongs to, so for all constraints which belong to the active set of x, then this particular condition, this particular dot product should be less than 0, and this direction d will give me a decent feasible direction. And since this, and again this particular set is not the like the entire range of feasible directions. So it's just a subset of the set of all feasible directions at x. Okay, so this is also an important lemma. So these two so these two sets, basically d bar and f bar, help us to um, algebraically depict how my d should look like, or the feasible and the descent directions should look something similar to this. So the intuition behind this particular lemma is, suppose this is my constraint set, right? And so the gradient of the constraint at this particular point, let's not consider it like a complete. So at this particular x, oh sorry, let's consider this is my active constraint at this particular point, right? um, and this side is basically my feasible direction side. So the gradient of h at this particular x looks something like this, right? So all the feasible directions should make a obtuse angle with this. So basically h transpose d should be less than 0, will give me feasible directions. So if you want, I'll link down the proofs of both the theorem that I have mentioned earlier and this particular lemma. If you're interested, just let me know. Okay, so now if you remember, uh, we had the theorem stated that if we want a feasible direction, then basically, or if we are at a local minima, then the set of feasible directions and the descent directions, the intersection of both of them is a null set. So if d bar is a subset of d and f bar is a subset of f, then by theorem 1, I'll say theorem 1 now, because there's just one theorem right now. So by theorem 1, f of x intersection d of x is a null set, right? So f bar of x intersection d bar of x should also be a null set, right? So the result is that if my x star, sorry, here it should be x star, and x star. So if my x star is a local minima, then f bar of x star intersection d bar of x star is a null set. Okay, so let us see an example in this case also. So suppose I have to minimize, just change the color. So suppose if I have to minimize x1 square plus x2 square subject to x1 plus x2 less than equal to 1, x1 greater than equal to 0, and x2 greater than equal to 0. So my feasible set will look something like this, right? And if I consider this particular point, say xa, then this particular at this particular point, the only constraint that is active is this particular constraint, which is this. So I'll just take a the gradient of h at this particular point, which is 1 comma 1, right? And if I have to see the feasible direction, then the set of all d's basically which form this is my, sorry, not a decent direction, a feasible direction. So the set of all such d's will give me some subset of feasible directions. So basically let's suppose my d has d1 and d2 as elements. So for all d1 comma d2, that d1 plus d2 is less than 0 will give me a set of feasible directions actually. So in this particular case, these directions will give me feasible directions basically. Okay, so yeah, and if you see, this is my objective function. So the objective function contours will look something like this, right? So if I take this particular objective, then the set of descent directions d will look like f transpose x times d should be less than 0. So again, in this case, gradient of f of x equals to 2x1 comma 2x2, right? So for all d1 comma d2, 2 twice of x1 times d1 plus x2 times d2 should be less than 0 is the set of all my descent directions. So now if I have to so basically if I have a local minima which if I visually inspect, I'll see that this particular case is the origin, right? Then I should find that x star f bar of x star intersection d bar of x star should be a null set, right? So let's see this. So at x star basically in this case, which in this case is 0 comma 0, again, so my feasible direction does not really depend on x, so it'll look like d1 plus d2 less than 0, a set of all such intersection, set of all d1 d2 which satisfy this. So basically if my at x equals to 0, x star equals to 0 comma 0, this particular term and this particular term will make the entire thing 0, and thus making d bar as a null set basically. So this obviously will give me a null set. So this was just one example which demonstrated that if I am at a local minima, then this particular condition is always validated. So you should note that this is a necessary condition basically, but not sufficient obviously. So in the next sub lecture we'll talk about KKT conditions, which will basically give me some conditions on how to solve constraint optimization problems. Okay.